In this example, I'm going to look at what happens when we expand a high-pressure gas, in this case ethane, into a vacuum. We start with the ethane constrained by stops that prevent this frictionless piston from moving to the right. It's well insulated, so there's no heat transfer. Because there's a vacuum and a frictionless piston, then when we remove the stops, there's no work being done. And the question is, what's the final temperature and the final pressures? But we want to treat this as a real gas. And we're given that the volume of this vacuum region is 3 times the volume on the left side of the container. So it's a closed system, and we can apply the first law for a closed system, meaning no mass transfer in and out. So delta U is Q plus W. There's no work, frictionless piston, weightless, no resisting pressure because of the vacuum, well insulated, so there's no heat, and so delta U is 0. If this were an ideal gas, delta U equals 0 means delta T equals 0. However, because it's a real gas, that's not the case. We're changing the interactions between the molecules as we lower the pressure. And so what we're going to use is the Ping-Robertson equation of state. So here's the Ping-Robertson equation of state, where the pressure now is related to density, which is the inverse of the molar volume. And there are two constants, A and B, where these constants are a function of the critical pressure, which is 4.88 megapascals for ethane, critical temperature 305.4 Kelvin, and the eccentric factor 0.099. So I won't write down the details, but essentially we can calculate A if we know these 3 parameters, and we use a computer program to do this and solve for conditions, because we also have to use a computer program that can calculate the internal energy from the equation of state. And so what we're going to do then is first use the equation of state to calculate our initial volume and to calculate the internal energy. Once we have that, it means we know the final internal energy. We know the final volume is 4 times the initial volume. So we have 2 state properties, volume and internal energy, which means we have a unique value for the temperature and the pressure. And so we use a spreadsheet equation of state program that's described in a separate screencast. And that has to iterate to find the correct values for temperature and pressure subject to these 2 constraints. And it does that to find that the temperature is 391 Kelvin. The pressure is 6.52 bar. And it did that by using the critical values to get the constants to substitute in the equation. And you'll notice that the temperature does change, decreases slightly, contrast the ideal gas law, and the pressure is not just 1/4 of the original pressure, as we also would expect from the ideal gas law. And so the equation of state then accounts for the interactions between the molecules in this adiabatic expansion.